When we talk about blockchain, one thing that is really important, one building block, are hash functions. They are used for the transaction, verification, authenticity. They are used when you're referring to individual blocks. They are used in the consensus protocol. And it turns out that it's not just important for blockchain, but that hash functions are actually used in many different applications throughout our economy. And that's exactly what we're going to look at right now. All right, let's get started with a quick definition of a hash function. Now, a hash function is actually something quite easy. Intuitively, you put something in there, input or pre-image. It can be of pretty much any length. There is a mathematical limitation, but it doesn't matter for all practical purposes. And what you get once it is in this map function is an output of a fixed length, okay? So basically, it's a mapping algorithm. You put something in there, and it maps it to a result of a closed set, the result of a fixed length. So a little more formally, you have a function, uppercase H, the pre-image M, it's basically the input you put in there, and then it results in a hash value H. So it's a mapping function, capital H of M, that maps it to lowercase h, the hash value. And that's really it. I mean, there are many different versions of hash function, as you will see, but that is the basic idea. You're mapping something of a quasi-arbitrary length to a result that is of fixed length. Now, note that's not a cryptographic hash function. We will talk about that later on in this lecture. That's just a regular definition of a really simple, really basic hash function. Now, in most cases, when we talk about applications, of course, there are more restrictions. So these applications I mentioned here mostly employ cryptographic hash functions, the ones we're going to talk about later on. But just in general, it's unbelievable in how many different applications hash functions are actually used. For example, in terms of data protection, when applications store user passwords, they don't store them with clear text. That would be really bad from a security practice point of view. What you're doing is you're only storing the hash values, which gives you some additional security in case your server gets hacked. Then, of course, in verification and authentication, for example, in the case of Bitcoin, you remember all of these identification numbers for the transactions and the blocks. You will see why it also can be used for verification and authentication. Quick teaser, it's because when you change something just a little bit, it will result in a completely different hash value. But I have an example in this slide deck where this will become quite obvious. And then, of course, proof of work in the case of Bitcoin, the consensus algorithm is entirely based on these hash functions. And that's also why it is really important to understand what a hash function actually is before we can talk about these things. Then data lookup optimizations, again, the blocks, the transactions, they have their hash value based identification numbers. As you have seen in the last slide deck, that was a way how you could get the data, how you could ask for it, how you could request it in terms of their hash value, and that's exactly what it's used for. And then error detection, many checksums are actually based on simple hash values. So checksums, for example, I have an example in here with the IBAN, and that you will see later on, where when there is a typo in there, people will realize that because the checksum changes and it doesn't match to the contents anymore. So these are just a few of the applications. As I said, it's used in so many different applications. It's something, even if outside from blockchain technology, it's something you should be aware of, something you should understand to some extent, and that will be really useful. Okay, so one thing you have to understand first, and I assume many of you already have some background with modular arithmetic, is these operations right here, the mod operations. And in case you have never seen that and you think it looks quite complicated, it's not. It's in fact really easy, and most of you will have done this in kindergarten actually, or at least in elementary school, before you even realized that you actually done something like that. The idea is you're dividing a number, and instead of looking how many times you can divide it, what you usually do is you only care about the remainder. So you only care about what is left. So one example, when you have 8 mod 7, then you can divide it 1 times. 8 divided by 7 would be 1, but you don't care about that, you throw it away. But what is left is 1, because when you divide it 1 times, it would be 7, right? And then 1 is left, and that is your result right here. Here, 2 plus 3 is 5. 5 mod 7, you can divide it 0 times. What is left is 5. 2 to the power of 5, so that would be 2, 4, 8, 16, 32. 32 mod 5 can be divided 6 times, then you would end up at 30. The remainder is 2, so the result of this mod 5 is 2. Okay? And really what you're doing in this case is you're just circling around this modular clock. Okay? So this is basically the potential solution space. When you have mod 7, then it can be any result between 0 and 6. And once you cross 6, then you would start at 0 again. So you can just count around that clock. Count, 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 count. For example, when you had these 32, you just, okay, here it's mod 5. So that's not a valid case for mod 7 here, of course. But when you think about that, you could have a mod 5 circle, a mod 5 clock. Then it would just circle around, circle around, circle around, circle around these 32 times. And then you would end up at 2. That's the idea. And these mod operations, they are really useful to create so-called one-way functions, and that's a concept that is heavily used throughout cryptography, of course. Now, using that, you could build a really simple hash function. What you could do, for example, is you could say, okay, we have a message, mod 12, that results in the hash value. So message in this case is just a number. And this example accepts any numeric preimage M and returns a corresponding hash value that is element of 0 to 11. Obviously, when you think of the clock again, 0 to 11 when you have mod 12. So that's quite easy. That's something we will use a lot in this course. So even though it's quite simple, you should get used to it. Now, a really simple application, as I've mentioned, for hash functions are checksums. Checksums, of course, they are quite useful because whenever something is typo prone, for example, with an account number, as in this case, and a typo could potentially have catastrophic consequences, you better put a checksum in there. And one of the best known examples is the IBAN, the international bank account number. So that's basically for international payment instructions, also for domestic payment instructions in many cases, the number you use when you want to transfer some money to somebody. The way it is created, the IBAN, from the domestic account numbers, from the traditional account numbers, is you use the bank code, you use the account number, and you get something that is usually referred to as BBAN. Then you append the country code and 00, which is the empty checksum right here. And you replace any letters with a number that corresponds to 9 plus the position in the alphabet of that corresponding letter. Now, in most cases, it's just the country code, but there are actually all account numbers that include letters also in the account number. And in that case, you also switch these. Then you perform the modular 97 operation on the number. So in this case, you have this number right here, mod 97, and you would end up in this case with 42. And you subtract that result, these 42, from 98. So 98 is just the number you take. That's hard coded in the algorithm. You subtract the result and you get your checksum. Okay. And the great thing about this is whenever you have a typo somewhere in here, so when somebody messes up one of the positions, one of the characters in the account number in the IBAN, then there is a really high probability that it just will not match the checksum anymore, that you can identify that there is a typo in there, which is especially useful, for example, when you're using online banking, you're typing something in there and then you mess up with the number you got from a payment slip, for example. Then your online banking will in many cases be able to tell you that this is an invalid IBAN before you even send the payment, which is of course great. And there are similar approaches, for example, with credit cards, with vehicle identification numbers in the US and Canada, with radio protocols to make sure that everything got transmitted correct, and communication, where you have parity bits. So basically where you have bits, individual ones that check if a certain package is actually corresponds to the actual data or has any mistakes in there. Now, what's really important to differentiate is this is helpful for accidents. So, as I said, when there is a typo or when something goes wrong, then you will, with a very high probability, find out that something just went wrong. But it is not useful, these simple hash functions, to prevent attacks. For example, here in both cases, that's the original IBAN and that's the manipulated one. Both of these have a checksum of 56, and it's actually quite easy to come up with an IBAN where you change some of the characters and still end up with the same checksum. So that's not to prevent an attack. A dedicated attacker could still manipulate the IBAN in a way that would result in the same checksum. It's really just for typos when something goes wrong by accident and somebody didn't take care. That just messes up with some of the letters or some of the numbers, okay? For security purposes, these simple hashes are of limited use, and there you need something else. And that's when we come to the cryptographic hash functions. The additional criteria for cryptographic hash functions that they have to be approximately uniformly distributed in terms of the hash value. So a hash function wouldn't be that useful if it always ends up with the same hash value. That would be a really bad idea. Also, they have to be relatively quick to compute for any given pre-image. It wouldn't make too much sense when a single computation would take up a lot of time. Also, there shouldn't be too much of a difference between larger pre-images and smaller ones. And it must be a trapdoor function. So it should be infeasible to generate pre-image from a hash value. And when you look at a certain hash value somewhere, there should be no way back, okay? And that's really the idea of this trapdoor function. That's also what we use mod operations and other nonlinear operations to make it really hard and not feasible with our current understanding of math, with our current knowledge, to go back, okay? It's really this one way. Pre-image to hash value, yes. Hash value to pre-image, no. And that's also important for the cryptographic hash functions. Then the Avalanche Effect, small changes in input results in totally different output. It's seemingly random, so when you just change a little bit, one position, it creates this complete chaos. And it creates a completely new hash value, something that doesn't look in any way similar to what you had before. So it seems to be random. In fact, it is of course deterministic. So when you put the same input, the same pre-image in there again, it will lead to the same result. So it is deterministic, although it looks random. But what is important is this Avalanche Effect. So when you just change a little bit about it, it will give you a completely different result. And then last but not least, a very low collision probability. It should be infeasible to find two distinct pre-images that result in the same hash value. So the space, the potential solution space, must be large enough that this cannot, in theory it can always happen, but you cannot force it to happen, and you shouldn't be able to feasibly find one of these collisions. That's really important for cryptographic hash values. And of course, when you have this limited space, as with our mod 7 example, when you have 7 potential solutions, it's quite easy to brute force. You can just try it out. So the solution space, in this case, the space of potential outputs of potential hash values has to be much larger for a cryptographic hash function. In Bitcoin, there are 2 hash functions that are heavily used. The first one is SHA-256. In many cases, it's done twice the operation, so it's double SHA-256. And you have RIP-EMD-160. Now, SHA-256, as you would expect from the name, results in a 256 hash value, 256 output, and RIP-EMD-160 results in a 160-bit output. So the example of the Avalanche Effect in SHA-2. You have SHA-2 and then the pre-image right here as the function, and we say, okay, let's go with this is the pre-image as the actual pre-image, so we put the text in there. Then you would end up with something like this, okay? So that would be your resulting hash value. Now, for the non-computer scientists, don't get confused by the letters in this number. That's just hexadecimal, base 16. And base 16 uses besides O to 9 also the letters A to F. It's quite easy to map to bits. Each letter corresponds to 4 bits. So for example, 0000 would be 0. and 1111 would correspond to F as an example. So you have, at each position you have 16 possibilities, and that's just a more compact way to write the information. But at the end of the day, it's just your regular number. So you could also, instead of these 64 alphanumeric characters, you could also use the 256 bits and would be the exact same information. Anyways, what I actually wanted to say is, when you're changing just a little bit from the pre-image, so instead of a uppercase T, you lose a lowercase t, then you have this avalanche effect, and the resulting hash value looks completely different. So as you can see, everything that is in red changed. The rest, these 8 right here and this A, just stayed the same due to pure probability. I mean, when you have 16 possible characters for each position, some of them will remain the same, some of them will stay unchanged just by sheer luck. But as you can see, this minuscule change really led to an avalanche effect, where so much of the hash value actually looks unrecognizable. It completely changed, and it seems random, although it is deterministic. Now, what is important is the nonlinearity. There are choice, majority, mod, rotation, and shifting operations in there, and it's really efficient to compute with a computer. But when you do it by hand, then you get around 0.67 hashes per day, and of course you will have many errors in there, so you can throw away your work, because there is no way you're going to do all of these operations throughout the entire day without making any mistakes. That's just, I can't imagine that this is going to happen. If you want to see what I'm talking about, there is a person, Ken Sharif, who actually did that by hand. So you want to see somebody computing a hash value by hand and get an understanding of what is done. This is a fantastic video right here, and it gives you some understanding of what is actually done when you compute these hashes, and why it is so hard, why it is infeasible to go back when you have a hash value to the pre-image, why it is a trapdoor or one-way function. So the low collision probability we talked about. Of course, as I said, in theory, since there is a finite set, since there's a closed set, there will always be collisions. I mean, when you have a certain set of potential solutions, but quasi-unlimited input values, then of course there will be collisions. We know that for sure, that in theory there are collisions, but what must be infeasible is to find these collisions. So the collision probability must be so low that, first of all, it doesn't happen just at random, but also when people are actively searching for it, they cannot achieve this. Okay, that's the idea of this low collision probability, and that's a really important property of cryptographic hash values. So in SHA-256, you have all possible combinations of these 256 bits, which is 2 to the power of 256 potential hash values. In base 10, this corresponds to this number. I have no idea what this number would be called, but it's just this really long number that doesn't even fit on one line in our usual number system, base 10. Okay, and it gives you some understanding of how many potential candidates there are, how many hash values there are, and why it is so hard to find a collision. Now, if you want to find a collision, let's not go with the entire hash value. Let's try it step by step, and that will actually be really important, what I'm about to show you now, for mining, for the proof of work algorithm employed in Bitcoin. So what we're trying to do now is we're trying to set some of these positions to 0 and find hash values that correspond to the adequate number of zeros, the number we're looking for. Okay, so when we're saying, okay, we're looking for a hash value that starts with a 0 in hexadecimal, and of course there in hexadecimal, as I mentioned earlier, there are 16 possible characters, alphanumeric characters per position. Then you would have a probability of 1/16. Okay, when you want to be when you fix the first number right here, when you're saying I want to be below this threshold value, this would be a probability of 1/16. Now, if the first position and the second position at the same time need to be 0, then you would have a probability of 1/16 to the power of 2. Okay. If the first three positions have to be 0, it would be 1/16 to the power of 3, and so on. So you can see how this probability goes down quite quickly, how it escalates quite quickly. And that's the idea. That's something, as I mentioned, that will be employed in the consensus algorithm of Bitcoin, but also shows you how fast the probability of this collision actually goes down. Because, I mean, when we talk about collisions, then essentially you can set all of these to 0. That would be a collision. That would be, or that we are looking for a specific hash value, and that's just completely infeasible. Now, you can program that. For those of you who have a programming background, your goal would be find a nonce. A nonce is a number only used once. That's something that gives you variation. Together with a fixed input string, so that would be your pre-image, returns a SHA-256 hash with preset characteristics, in this case, number x leading zeros, okay? So you take the input, that could be your name or whatever, the pre-image, and add a nonce. You concatenate it starting at 0. So and then you compute the SHA-256 hash value from your input pre-image plus nonce. So, the input plus nonce. So you concatenate that. That would be your pre-image, because you also need the nonce, of course. And then you compare the resulting hash against the minimum number of zeros. There would be a decision. If the criteria is not met, you increase the nonce by 1 and return to step 2. So you basically cycle back. And if the criteria is met, then you return the hash, the nonce, and the time it took to find it. So you would be in this loop until you find a feasible solution, until you find a solution, until you find the nonce that actually corresponds to the required number of leading zeros. If you want to see an example script here in Python, then you click on this link. There you can play around with it and you can test it out, and you can actually check how long it takes to find these zeros. For the first few leading zeros, this won't be a problem, but once you get to larger numbers of leading zeros, your computer fan will start rotating quite heavily, and you will not find any solution in any reasonable time frame. All right, 2 books I can recommend. First one, this is used quite heavily throughout the class, also in our crypto lectures later on. It's a fantastic book. It's quite easy to read. It's the code book by Simon Singh. And then you have the Introduction to Modern Cryptography. That's a great book for those who like it a little more formal. So it's not as easy to read. It's still relatively simple. I mean, it's also a great book, and but it's a little more math heavy than the code book. The code book is really just storytelling. It gives you some introduction to cryptography. I think both of these are great companion books. Of course, for the University of Basel students, they are not relevant for the exam. But if you're looking for further reading, that would be something you should look into. All right, that's it. Stay curious. See you soon.